cloud. All right, so I guess we'll go over the key. This is to form A. I think the true and the false in both forms was the same. I can't remember. The pattern was true, false, true, false, true. You want me to explain why any of them are what they are? I don't care. So the first one, that's just the definition of a discrete probability distribution. I told you to know that. The second, a binomial distribution has an unlimited number of trials. That is false. It has a set number of trials. C, the standard deviation, the standard normal distribution has two parameters, the mean equal to 0 and the variance equal to 1. So some of you put false. You said the standard deviation is 1, but if the standard deviation is 1, then obviously the variance is 1 because 1 squared is 1. If the calculated z-score is negative, then the data value x is greater than the mean. That should be is less than the mean. For a continuous random variable, the probability of any single outcome is 0. I told you that in class. Then, are there any questions over that part? Awesome. Number 6, approximately what percentage of normally distributed data values fall within the 3 standard deviations of the mean? That's just using the empirical rule, 99.7. Number 7, the maximum likely difference between the point estimate of a parameter and the actual value of the parameter is called the margin of error. Just the definition of it. For a binomial random experiment that has 8 trials and the probability of success is 0.45, what is the mean? So this is n, this is p. The mean of a binomial is just n times p. So if you do that, you get d 3.6. So the first page was worth a total of 19 points. Second page, when the population standard deviation is known and the sample size is greater than 30, which critical value should be used to calculate a 95% confidence interval for the population mean? I think on form B, it says is less than 30. If you have the blue one, it doesn't matter either way, because if you know that this is a population standard deviation, you still need to use a critical Z value to calculate the confidence interval. Number 10, as the sample size n increases, what happens to the standard error of your estimate? It decreases. I mentioned that in class. Standard error is sigma over the square root of n, and if n increases while sigma stays the same, that value decreases in quantity. I'd never put these on the exam before, and I saw it on someone else's, so I thought I'd put them on here because they're kind of easy. Find the area under the standard normal distribution curve for each, 1 point for drawing the curve and shading the area, and 1 point for the numerical value. So all you have to do is draw the z curve and then look at the area that you're interested in. So you're interested in the area between the z-scores of minus 2.27 to 0.22. So you needed to shade that area here, and then use the rule that the probability of it being in between two z-scores, the probability of it being less than the upper, minus the probability of it being less than the lower. And it gives you an answer of 0.5755. For number 12, use the same idea. It's just saying the probability of z being greater than 2.89. So you want the area on the right-hand side of 2.89. But the table will give you the left-hand area. So take 1 minus the left-hand area to give you the right-hand area. It will give you 0.0019. Then this is just the reverse of it. I'm telling you the area of interest, and I want you to find the z-score. First one, the probability of z being greater than z naught is 0.0793. So that means the area to the right of some unknown z-score is what it says, 0.0793. So then look at the area to the left of it, and that'll tell you the corresponding z-score if you look at it in the table. So 0.9207. And this was actually one of the ones that is dead set in the table, and I did that on purpose. So it's 1.41. Some of you gave me minus 1.41. That would be if this was the left-hand area, if 0.0793 was the area in the left tail. Number 14, the probability of z being less than z naught is 0.0078. So it's going to be somewhere down here since the area to the left of it is so small. then all you have to do is look for that area in the table. And if you do, the corresponding z-score is minus 2.42. I think this one was the same on both exams. The County Highway Department recorded the following probabilities for the number of accidents per day on a certain freeway for 1 month. The number of accidents per day and their corresponding probabilities are shown. Part A, find the value that makes the distribution above a valid probability distribution. So all the probabilities are obviously between 0 and 1. So all you need to check is what makes them give a sum of 1. So the sum of the probabilities, you just add all these three together and set it equal to 1 and solve for K. If you do, it should be 0.1, not 0.01. I don't know why I did that, but K is 0.1. Don't worry, I didn't mess up grading that on your test. Find the mean, the expected value. All you do is take the sum of the x's times the corresponding probabilities. So if you plugged in K as 0.08 here, wherever it is right here, I still counted it right because like it said, if you don't figure out this part, you can assume K is this. So if you use these values, K is 0.1 and the rest of those, you get an expected value of 2.2. If you use K as 0.08, you get an expected value of 2.18. Then part C, find the variance. So this part is obviously where everyone messes up. It always will be. So the expected value of x squared minus the expected value of x, that quantity squared. So first you need to find the expected value of x squared. You just do that using the same idea that you did up here. But all you do is square these x values here and then add them all up. If you do that, you get 7.8 as the expected value of x squared. Some of you gave me that as the variance. That is wrong. So you need to take the expected value of x, what you computed in part B, and square that and take that off 7.8. If you do that, you get 2.96. I can't remember what you get if you did 0.08. Number 16. A survey found that 20% of people believe they have seen a UFO. Choose a sample of 11 people at random. Find the probability of the following. Round intermediate calculations and final answers to at least 3 decimal places. The first part, at least 3 people believe that they have seen a UFO. So that means you're interested in the probability of X being greater than or equal to 3. Some of you did the probability that X is less than or equal to 3. In that case, what you need to do is you could either take the probability that X equals 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 11, or you could take the complement. So just 1 minus the probability of X being less than 3. As it's a binomial random variable, it can just take on values 0, 1, and 2. And all you do is find those probabilities in the table, add them up, and take 1 minus them. I'll give you 0.383. If you did it on the calculator, I think you get something like 4 or 5 decimal places. I just did it from the table. Part B, 2 or 3 people believe that they have seen a UFO. So these 2 events are mutually exclusive. They can't happen at the same time. So you just add the corresponding probabilities. The probability that X equals 2 plus the probability that X equals 3, and you get 0.516. And then this one, part C, exactly 2. It's just look at 2 in the table. If you had form B, I think the percentage was 25%, if I remember right. And it gives you almost the same thing. This one, or half of you got beaten. This was actually, all of the free response questions were actually homework questions. A mandatory competency exam for high school sophomores has a normal distribution with a mean of 400 and a standard deviation of 80. Round the final answer to the nearest whole number and intermediate Z calculations to 2 decimals. The first one, the top 5% of students receive $500. What is the minimum score you need to receive this award? This idea was kind of like one of the problems that I told you to look at in your notes. I emailed you the day before the exam because I forgot to mention it. But if you watched one of the videos that said extra help, I actually showed you how to do the problem. So all you need to do is look at the corresponding Z-score with area to the right of 0.05, because that would be the top 5%. If you do that, then the actual Z-score, I said you can take either one of them So one of them says 0.050 or 0.9505. The other says 0.9495. And I said take either one. So if you take 1.65, then you set this equal to some data value x, which is the minimum minus the mean over the standard deviation. Then you solve for x by multiplying by 80 on both sides and adding 400, and you get 532. I can't remember what you get if you do 1.64. I think it's maybe the same. It may be close. The next one, the bottom 4.5% of students must go to summer school. What is the minimum score you need to stay out of this group? So the idea is still the same, but in this case, we're looking at the left-hand area here. And the area to the left of some z-score is 4.5% or 0.045. And if you look for that area in the table, you get a z-score of negative 1.70. Then use that z-score formula again to solve for x, and you get x is 264. Everyone okay with that? This one, I think I changed the number of hours worked and the standard deviation for Form B. It's pretty much almost the exact same. I think it says 44.7 and 3.5 or something like that. I don't know. The first step, find the sample mean. I didn't expect you to write out everything. So literally all I did was write down what it is. The sample mean is a sample number or the average number of hours worked per week for registered nurse, 43.7. The critical value, so in this case, I say the standard deviation of the sample. So you need to use a critical T value with 90% confidence and a corresponding degrees of freedom of what? Degrees of freedom is equal to n minus 1. 18 minus 1 is 17. So it's 1.740. Then calculate the standard error. That's just S over the square root of n. S is 2.5, n is 18. So it gives you a standard error of 0.589. Then calculate the margin of error. That's just the critical value times the standard error. So 1.740 times 2.5 over the square root of 18. And that gives you 1.025. Any questions up to there? Then the final part, give the confidence interval. All you do is take the point estimate that you get in part A plus or minus the margin of error that you get in part D. If you do that, you get 42.675 to 44.725. Then the interpretation. So I said no, how to interpret it because it was going to be on there. We are 90% confident the mean number of hours in RN works is between 42.675 and 44.725. So it should say per week in there, but I wasn't that picky. The last question. Also, if you watched the extra help video or you were actually in there, I showed you how to do this one as well. I actually showed you how to do it in class too. A pizza shop owner wishes to be 98% confident or to find the 98% confidence interval of the true mean cost of a large plain pizza. I wonder what they mean by plain, like nothing on it. How large should the sample be if she wishes to be accurate within 13 cents? A previous study showed the standard deviation of the price is 25 cents. Round your answer to the next whole number. Using this, you can identify what is E and what is sigma. So in this case, we want to be accurate within 13 cents. So E is 0.13. Sigma is 25 cents or is 0.25. Z alpha over 2, you had to find that. So what you had to do was look at the area in between two z-scores is 0.98. That means that 0.02 area is left in both tails added together. Therefore, 0.01 is in each tail. And then all you have to do is find the associated z-score on this side. If you do that, you get the negative z alpha over 2 is negative 2.33. Or you can just say the positive z alpha over 2 is 2.33. And all you do is take these three and plug it into the formula to find the minimum sample size. That gives you 2.33 times 0.25 divided by 0.13. Take that and square it. You get that, you get 20.07. So round it up to 21 since the decimal. Everyone okay? Okay. So was it that bad? The next one's a little bit shorter. I'm debating if I just want to put a freebie question on there because someone else did last semester. They made it easy for their students. I did. Anyone online, you have any questions? Awesome. Okay. Let me get these markers out and then we'll start where we stopped last time. Okay, so what did we talk about last time? Yeah, hypothesis testing. And all we started talking about was how to identify the null and the alternative hypothesis. So the null hypothesis is what? You just want to use the definition. It's basically the statement that says there's no difference between a parameter and a hypothesized value. And then the alternative is there is a difference. I didn't talk about this last time, but the general form of a hypothesis test, or the general form of the null hypothesis that we'll use if we're testing a population mean, mu is equal to mu naught. And then I can't remember if I used H1 or HA. What does it say, H1? And H1 could be mu that does not equal mu naught. It's greater than mu naught, or it's less than mu naught. So I'm just mentioning this part now because it's going to come up today. We call the value that it's equal to another null hypothesis the hypothesized value. Then we talked about a couple of examples last time, just identifying this. It says, note the hypotheses in this example only portray a hypothesis test of the population means mu, because every hypothesized value we had was a mean, and we were testing that, or wanting to test that. And it says the purpose of a statistical hypothesis test is to see if there is sufficient evidence from a sample to support something about the population. For example, suppose we wish to determine if the mean GPA of all OSU freshmen is greater than 3.0. Here, the statement, the mean GPA of all OSU students is greater than 3.0 would be what we know as the claim. So it's basically what they're stating is true. Because of the directional sign, the greater than symbol. This claim should be stated as the alternative because it indicates there is a shift or change in a population parameter. In this case, the population mean. Then it says, what would our hypothesis look like? And in this case, null hypothesis and the alternative. The null is that mu equals 3.0. We're just saying that the average GPA of freshmen is 3.0. And the alternative would be, we're claiming that it is greater than 3.0. So mu would be greater than 3.0. And in this case, the alternative is what we claim. So on your homework, it's going to have you identify the claim and not the claim. Most of the time, the claim will be the alternative. Sometimes it will not. And let's look at an example where it is not. Let's consider another example. A study claims that the undergraduate students take an average of 50 milligrams of Adderall during finals week. Is that a decent amount or not? I don't know. Oh, great. Yeah, I have no idea. It's just whatever I was putting in the notes. So I don't know. So an undergraduate student runs a hypothesis test to see if this is true for students at OSU. Then what would the null hypothesis be? Mu equals what? 50. And the alternative would be, what do you think? Yeah, correct. It doesn't say it'll be greater than 50 milligrams or less than, so it's not equal to. And in this case, which one is the claim? The null, because it's saying, in this case, a study claims the undergraduate students take an average of 50 milligrams. So it's claiming that value. Yep, basically. Then here it says, notice the statement, students take an average of 50 milligrams during Adderall during finals week is the claim, but we represent it in the null hypothesis. And it says why? Because the alternative indicates a shift or a change in the population parameter. So therefore, we don't want to put mu equals something in the alternative hypothesis. Then blah, 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 blah. You don't need to know about that. Now we're talking about decisions. Funny enough, I'm actually taking a test today where we have to do hypothesis testing, but the computer software does it instead of me. So the first one, if there is not enough evidence to support the alternative hypothesis, then we will say we failed to reject null hypothesis. Not enough evidence to support H1 implies we fail to reject HO. And then it mentions, why can't we accept the null hypothesis? And it says it in your notes because I just put it there, because we are gathering evidence in support of the alternative. We're trying to prove the null wrong. Then, if there is not enough evidence, implies that we failed to reject. If there is enough evidence to support the alternative, then what do you do about the null hypothesis? Obviously, you would reject it. If enough evidence to support H1, that implies reject the null hypothesis and support the what? Yeah, support the alternative. So in your filled in notes, I actually write out H1 and HO as null and the alternative. It doesn't matter. I mean the same thing. Now, know this next part. Because our evidence is based off sample data, when we make the decision of rejecting or failing to reject the null hypothesis, there may be a possibility we made an incorrect decision. What is the only way you can get a truly correct decision? What do you think? The only way to prove a claim is to sample what? The entire population of interest. Know that. I think it comes up later in here, but I just thought I mentioned it now. Did I already fill in these tables below or not? Okay, cool. Good number. Then, since we could make an incorrect decision, we will talk about two types of error. And we will say one is called type 1 error and the other is called type 2. You'll probably need to know the definitions of these. Your homework questions you over them as well. So type 1 is when you reject a null hypothesis when it is actually true. So that's for type 1. And this has a name. It's called the significance level. Significance level. You've actually seen it before. It's alpha. Then the other type of error we can make is called type 2. So if whenever we reject a null hypothesis when it's true, the opposite of that is failing to reject a null hypothesis when it is actually false. Then, in the other two cases, it's a correct decision. Then looking at the decision table below, it says, should I draw the decision table up here or not? I don't care. Cool, great. Then on the left-hand side, it says the decisions. So reject the null hypothesis or fail to reject. So if we reject the null hypothesis when it's true, that's just a definition of type 1 error. Then going to the right, if we reject the null hypothesis when it's actually false, that means we did a correct thing. You rejected it when it wasn't true. That's a correct decision. If you fail to reject a true null hypothesis, that's a correct decision as well, because it was already true and you didn't reject it. And then the last one, you fail to reject a false null hypothesis. That's just the definition of type 2 error. Everyone okay with that? So based on a decision we make or come to, you should know how to identify which error is possible to have been committed. Do you want to go over this court part or not? It's basically the same. It says looking at this from a criminal perspective. So you say you're innocent until proven guilty. Oh, I guess I didn't fill this part in. So what would the null hypothesis be in that case? Yeah, innocent. We're assuming you're innocent. And what is the alternative? You're guilty. Then we say if there is enough evidence to support the alternative, we say they are guilty and the defendant is convicted. They're going to the pen. Therefore, we have rejected the null hypothesis in that case because we had enough evidence to support the alternative. Therefore, we rejected the null. If there is not enough evidence to support the alternative, we say they are not guilty and the defendant is acquitted, or you can just say let go. And in that case, we didn't reject the null hypothesis because they were not guilty. So therefore, we failed to reject the null hypothesis. And then it says again, why can't we not accept the null hypothesis instead? In court, what are you trying to prove usually? Yeah, crime. So you're trying to prove someone guilty, so that's why. You want me to show you all this writing here or not? I don't care. That way, in case you want to write it down on the filled-in notes, here's what it says. Then using that same decision table, you come to the same conclusions, the same thing. Basically the same table again. Then the last thing, to clarify the type 1 error and type 2 errors for our example. So if we rejected a null hypothesis when it was actually true, that means we convicted a person that was actually innocent because they're going to prison when they shouldn't have. Then type 2 errors when we failed to reject a false null hypothesis. So that means the defendant was guilty, but we let them go. So acquitting a guilty person. You don't want to see the rest of it? That's right. There you go. That's all of it. Everyone online, you following me up to here? Great. One response. Am I good to move on, or you don't need me to keep going? Okay, good. So in this chapter, do y'all want me to do examples that are actually in here, or kind of homework type questions, or both? Both. Because the homework questions are a little more difficult than the examples. I have no idea. Excellent question. Let's look. I know chapter 9 has like 19. I don't know what chapter 8 has. Fair warning, once I start 9, you'll probably want to start the homework. It is the hardest one. Okay. I hate when they make you change the password. I don't know, it just irritates me. Okay, here we are. Sorry, people online. I'm looking to see how many questions are on chapter 8 homework. Is it actually open yet? I haven't looked. I think it is. Cool beans. Okay, so chapter 8 homework has 19 questions. So you may want to start. I think the first 3 or 4 are just basically identifying the null and the alternative and some definitions. Should I go over one of them? Cool, let's pick this one. I don't know where it is. Okay, people online, I'm going to show you the screen now. Share. Here we are. Okay, this is just a question from your homework. A hypothesis test is to be performed. Determine the null and the alternative. I think this is question 2. In 1995, the average duration of long-distance telephone calls originating in one town was 6.7 minutes. A long-distance telephone company wants to perform a hypothesis test to determine whether the average duration of long-distance calls has changed from the 1995 mean of 6.7 minutes. What is the null and the alternative hypothesis? C? That is correct. So the null, that mu is equal to some specified value, and in this case, we're saying it's 6.7. Then what we want to know is whether it has changed from that 1995 mean of 6.7. So it doesn't indicate whether it will have increased or decreased. So therefore, it is not equals to. So C. Everyone online, that makes sense to y'all as well? Okay, let's look at another one. Okay, I don't think we've talked about this yet, but you can probably guess. So in 1991, oh, it's basically the same thing. Okay, it's just asking what tail is it? You may not know this part yet. Yeah, it's two-tailed. If the alternative hypothesis is not equals to, it's a two-tailed test. If it's greater than, it's a right-tailed test. If it's less than, it's a left-tailed test. We'll talk about that here in a second. All right, let's go back to the notes. Turn this around again. Okay, this first one I already mentioned. The decision does not actually prove whether or not the defendant did or not commit the crime. Oh, this is just what it's saying. The decision is solely based on evidence. Then this means in statistical hypothesis testing, we base our decisions off of sample data, so we cannot actually prove the claim. This is just what I said earlier. In order to prove the claim, we would have to use the entire population, which in most cases is not possible. Everyone okay up there? I just wrote that up there earlier. Now it says, let's talk about a little bit more about these errors. The first one I already mentioned, the probability of type 1 error is called the significance level, or alpha. Remember last chapter when we talked about critical values with corresponding area of alpha over 2 to the left or the right? Basically the same thing here. Then the most common values of alpha are, I guess I'll just write them up here. Most common values of alpha are 0.10, 0.05, and 0.01. Now, by definition, what is the significance level? The probability of type 1 error. So that means when alpha is 0.1, there is a what % chance of rejecting a true null hypothesis? What's 0.1 as a dot? A percentage. 10%. Yes. So if alpha is 0.10, or yeah, alpha 0.10, that implies there is a 10% chance of rejecting a true null hypothesis. Then the next one says when alpha is 0.05, what is the percentage of the chance of rejecting a true null hypothesis? 5%. So I'm not going to write everything else down. We're just going to look at it like that. Same exact thing. Then the last one, when alpha is 0.1 or 0.01, what % chance is there of rejecting a true null hypothesis? 1%. What if alpha is 0.07? This isn't in your notes. Yeah, 7%. All you're doing is shifting the decimal 2 places to the right in that case. I'm going to write using that as a percentage. Then it says, like I said earlier, note, this is the same alpha we used to calculate the critical values in chapter 7 when we looked at confidence intervals. Now you'll need to know this next part, these critical values that correspond to alpha. So the critical values corresponding to alpha now determine what we call the rejection and another word for that is critical region. In our hypothesis test. That just means the critical values separate the fail to reject region from the rejection region. And then why do you think we call it the rejection region? You may want to know this definition as well. By definition, it represents the range of test statistics that indicate, golly, why does my handwriting always get so slanty? Indicate. Also, I need a new marker. There is a difference in the parameter and the hypothesized value. Then, so we reject the null hypothesis. So in short words, it's basically the values of the test statistic that indicate we are going to reject the null hypothesis. So what's that going to look like? Say, for instance, here you have a Z distribution. So we're going to look at what are called Z statistics or Z test statistics and T test statistics. So then we're going to be dealing with the distribution of the Z scores. And say we're doing a two-tailed test. So two-tailed, that means the alternative is of the form mu does not equal mu naught for some hypothesized value of mu naught. And that means we're going to have two rejection regions. We'll have one down here and one up here. And then what do you think the area in those two rejection regions added together will give you? What did it give us last chapter? Whenever we looked at the confidence level and the remaining area in the two tails, what was that value? Yeah, alpha. So the area in these two tails added together is going to give me alpha. Then the same idea is going to be the same as what we did last chapter. To find a critical value for a hypothesis test that's two-tailed, we're going to look at area of alpha over 2 to the left of some critical Z value. And that will determine the rejection region on the left-hand side. And we would reject the null hypothesis if we get a test statistic that falls within this region here. Then using the same idea on the upper end. If this is the negative Z alpha over 2, and this is the positive Z alpha over 2. And we will reject null hypothesis if a test statistic falls within this region too. So for a two-tailed hypothesis test, there are two rejection regions, one on the left tail and one on the right. And the area to the right of each of these critical values is alpha over 2. What happens if I look at just one tail? How will that change? You were actually looking at one tails on your exam. When I said the top 5%, you were just looking at the right-hand tail, right? You were looking at 5% falls above some z-score. Be the same idea there. You need to look at a corresponding test statistic or its corresponding critical value with area to the left of something you're interested in. And we'll talk about how to do that later. I just mentioned that now, so when we get to it later, you're not as confused. Have I lost anyone yet? Guaranteed I have, you just won't tell me. I do, indeed, from 3 to 4. Now, let's talk about what the test statistic is, or the general form of it. Then, the general form of a test statistic, so you can just call it test stat in this case, is what I say, is equal to the observed value minus the hypothesized value and then you divide this quantity. Gosh dang it, I'm going to erase that. So you take that quantity, you divide it by, what do you think? Whenever we found Z and T value, did we even do that yet? Yes, we did. So whenever we looked at Z scores of the standard deviation of the sample means, what was the corresponding Z score? X bar minus mu divided by sigma over the square root of n, right? And sigma over the square root of n was what? What do we call it? We actually talked about it in chapter 7 too. Then divide by the standard error of the estimate. The standard error. Then in this class, we're going to be dealing with tests for the population mean and the population proportion. So our observed values will be the sample statistics we can compute from each of those individually. So if we're doing a hypothesis test for the population mean, our observed value will be the sample mean. If we're doing one for the population proportion, the observed value will be the sample proportion, and we denote that p hat. We actually talked about that in chapter 7 as well. And then the expected value, which is the population parameter you would expect under the null hypothesis. Like I said earlier, you have mu is equal to mu naught. So that mu naught is what is known as the hypothesized value. And whenever we get to the population proportion, we'll talk about p naught, and that'll be the hypothesized proportion. Then we talk about the standard error of the sample means. In this case, the first one you know, or actually you know both of them, because you created confidence intervals for it. So the standard error of the sample means for the first one is sigma over the square root of n. The second, p times 1 minus p over n, take that square rooted. Okay, in last chapter, what was the standard error for the confidence interval for the population proportion? P hat times 1 minus p hat over n square rooted. So will it be the same in this chapter? Yes, it will. Then decision making. I guess we'll go through these 3. So there are 3 things you need to include in your decision/conclusion. So the first, statement regarding your decision about the null hypothesis. statement regarding your conclusion about the null hypothesis HO. What does that mean? Our two decisions that we can make are what? Yeah, so this means whether we reject or fail to reject. So reject HO or fail to reject HO. So FTR in that case just means fail to reject. In the second step, the justification behind your decision. So there's actually three ways you could have that. We'll talk about those later. And then the third one, your conclusion regarding the claim, making sure to put it in the context of the problem. So just like how we interpreted confidence intervals in this last chapter, you should know how to interpret the results of a hypothesis test. And will we talk about that? Obviously, yes, we will. Now we'll look at the different types of methods we will use to conduct a hypothesis test. So the first one is called the traditional or critical value method. So it's just like how I showed up there a second ago, whenever we had two critical regions determined by the level of alpha. It gave you two critical values. And if you had one less than one critical value, you rejected. If you had one greater than the other one, you rejected. So that's the idea behind this one. So the second one is the p-value method. We'll talk about how to do that later. And the third one, we actually did this last chapter, the confidence interval value method. So if the parameter estimate actually falls within that confidence interval, then we fail to reject. If it doesn't, we reject. We'll talk about that. First one, the traditional method. So the steps to perform a test for the hypothesis using the traditional method. So the first one, it's already said it there. State the null and the alternative. Number one. State HO and H1. Second step. State your decision rule. What does that mean? So that just means when using the traditional method, their decision rule depends on the type of alternative hypothesis. So let's look at the first one. If you're doing a right-tailed test, then you reject null hypothesis. If you get a test statistic, so test stat just means test statistic greater than the critical value. So if you have a right-tailed test like this, let's look at the Z one like we were talking about. If we have a right-tailed test, that means we're interested in the area to the right of something, right? Then you can find the corresponding Z-score with area of alpha to the right. And then we would reject for any test statistic above that critical value. That's the idea behind the first one. For a left-tailed test, what do you think it is? Yeah. So in that case, you would reject the null hypothesis. if you get a test statistic less than the critical value. That means if I had one down here, say here's my critical value for my left-tailed test, then all of these test statistics over here to the left would be where I reject the null hypothesis. Now combining these two together for a two-tailed test, what do you think it should be? So the way I write it, reject null hypothesis if the absolute value of your test statistic is greater than the positive critical value. Does everyone want me to explain why that is? So if I have two critical regions here, here's Z alpha over 2, and let's say negative Z alpha over 2 over here. So these two regions here represent my rejection regions, correct? So I'll reject the null hypothesis for any test statistic greater than this or less than this. But if this is less than negative Z alpha over 2 already, so that means it's more negative than this right here. When I take the absolute value of that, it will take off that negative sign and make it larger than Z alpha over 2. So then it would fall into this region over here if I take the absolute value. Does that make sense? Or should I write it another way? Let's say, or you can write it this way. Or reject null hypothesis if your test statistic is less than the critical value. This is the negative critical value because you're going to have a negative and a positive one. Or reject the null hypothesis if your test statistic is greater than the positive critical value. And that's just what it's saying here. I reject if I get a test statistic that falls within this region here or within this region here. How many people have I lost so far? Yeah, it'll happen. So the third part is actually the easiest. Calculate the test statistic. And 4, make a decision. And your decision should include all the parts we already talked about. The first one, statement whether you are going to reject or fail to reject, the justification behind why, and then your conclusion in the context of the problem. Then the second one we'll talk about is the p-value method. This one is slightly more difficult. So on your homework, whenever you do a hypothesis test for the population mean, when you know sigma, then it will have you find the p-value because your z-test statistic will be a z-score. So then you can find the associated probability of interest in the tables. For a t-test statistic, it will not give you an exact p-value unless you use the calculator. But it will give you a range of p-values from the table. And I will show you how to do it And I guarantee most of you will not get it because no one does usually. Now let's talk about the definition of what is a p-value. This definition is very weird. Holy cow, there's so much. We'll write it over here. A p-value is the probability. So I'm going to shorthand probability with prob of getting a sample statistic how does it say, or a more extreme sample statistic in the direction of the alternative hypothesis, in the direction of H1, given that HO is true. Whenever you first see that, you're like, what the heck? Even I was. So will it make sense right now? No, but it will whenever we do an example. Then let's look at this. Look at the example back on page 3. Recall we wish to determine the mean GPA of all OSU freshmen, or determine if the GPA of all OSU freshmen is it greater than 3.0 or not. Then say we take a sample of 100 students and find their average GPA to be 3.2. Then let's draw out what the p-value would be. So say here we have the distribution of X, which is the GPA of all OSU students. And we say it's going to be approximately normal. And under the null hypothesis, what is the hypothesized mean GPA? So in the middle here, we have mu is equal to 3.0, right? Then, if we want to know if we are going to be in favor of the alternative, then the p-value is the area under the curve that represents the probability of getting a mean of a GPA of 3.2 or higher. So in that case, it's 3.0. So say 3.2 is around here. Then, since the alternative in this case is H1 is mu is greater than 3.0, the direction of this sign greater than, it means to which side, the left or the right? The right. So that means we're interested in the area to the right of the 3.2 sample mean we got, right? Does that make sense? Then how will we find this p-value, you think? We have the distribution of, this would actually be X bar. We have the distribution of the mean GPAs. How would we find the associated probability of it being to the right of this? What do you think? What did we do in chapter 6? You turn this value right here into a z-score, and then you can look in the standard normal table to find the associated probabilities. The idea here is still the exact same. So that's just what it says right there. Then the steps to perform a test hypothesis using this p-value approach. The first step is still the same. State the null and the alternative. The second, state your decision rule. So this is the part that will change. And I will mention it here. So first one, if the p-value is less than or equal to the specified alpha that you want, then reject the null hypothesis. Then what happens if the p-value is greater than alpha? Yeah, just the opposite. Then, third step, calculate your test statistic and the corresponding p-value. So this part actually involves you doing something that the critical value approach already does. It calculates the test statistic, but then based on that test statistic, it finds the associated p-value, depending whether it's one-tailed or two-tailed. Then the last step is make a decision. Okay, at least I'll mention the stuff that we'll talk about now. So that was all for 8.1. Why is it not on here? There we go, sorry. Now, section 8.2 is going to be about z-test for the mean. So just like how we had that whenever we wanted to create a confidence interval for mu when we knew sigma, we used a critical t value, right? We're going to use a z-test statistic in this case if we know sigma. And how will we define that test statistic? Remember, the general form of a test statistic we had was the observed value minus the hypothesized value divided by its corresponding standard error. In this case, we're doing a hypothesis test for mu. So what is the expected value, or the observed value, my bad? The sample mean x bar. What is the hypothesized value? Mu naught. It's just the hypothesized mean under the null hypothesis. Now, what is the standard error? Sigma over the square root of n. And I guess I'll write what each piece is here. In this case, x bar is the sample mean. Mu naught is the hypothesized mean. Sigma is the population standard deviation. N is the sample size. Yeah, hypothesized mean. Still got 5 minutes, so we'll do a couple more things. Yeah, testing is given by this formula. Then some assumptions that must be made to do a z-test for the mean. You may want to know these. They may pop up somewhere. They may not. The population standard deviation is known. That one's fair game. If you know sigma, then what type of test are you going to do? Obviously, you're going to do a z-test because you know sigma. The second, the sample is random. Third, the population is normally distributed, or the sample size is greater than 30. If the sample size is greater than 30, what can you say by something that the distribution of the sample means is approximately normal? Anyone remember? Central limit theorem from chapter 6. Oh my Lord. Okay, I guess we'll talk about this last part, and then we'll get out of here. That way you can get started on your homework if you want. So critical values for this test are calculated using the standard normal distribution table. So if you have a left-tailed test, say left, I almost forgot to put a T in there, left-tailed. Then the critical value for this test is the z-score such that the probability of z being less than or equal to, let's call this z-score negative z alpha, such that the probability of z being less than or equal to this negative z alpha is equal to alpha. Second, critical value for a right test, for right-tailed. Critical value is the z-score. We will call this the positive z alpha, such that the probability of getting a z-score greater than or equal to z alpha is alpha. Or equivalently, the probability of z being less than or equal to z alpha is equal to what? That's just the area to the left of it. 1 minus alpha. We'll pick up there next time. If you came in a little late and you didn't get your test either last time or this time, it's up here.